Hello, it's Keith here, and this is lesson 7 of my Z80 programming tutorials, and this is the last of the Z80 series in its current form. Now, we're going to look at the last few major commands I think you're probably going to need to know in your programming adventures, but there are a few other rarer commands that are more specialized, and there's a lot of other things that it might be interesting for you to know, things like stack misuse, or things like binary coded decimal, depending on what you're going to try and do. But I do have a lot of other tutorials that cover those in the multi-platform series, and of course I have the platform-specific series as well, which will cover things like how to use your hardware. Today we're going to look at hardware a little bit. We're going to be looking at the ports. This is how the processor can send data and read data from the devices connected to the system, like the keyboard, the joystick, and control the sound and the graphics in a lot of cases. And so these are essential commands. We're also going to be looking at the LDIR type commands for block copying, and we're also going to be looking at the basics of interrupts. Now, interrupts is a very in-depth topic. It's a very advanced topic, but I thought it was something so essential to the processor we had to discuss it in some form, and we'll be seeing some examples of that today. Now, things like interrupts and things like ports are very platform specific, so we'll be looking at some general examples today on a couple of systems and discussing them in a broad sense, just discussing how the commands work and showing them by example. But if you want to see real in-depth stuff on how to do things on the individual systems, like graphics on the CPC, sound on the Spectrum, I've already covered that kind of thing in the platform specific series, so please go and take a look at that for the full ins and outs of that kind of thing. Anyway, let's go over to today's source code and let's take a look. Now, we're looking at the lesson 7 code today. You can see this is the lesson 7 file here we're looking at. And the first thing we're going to do is a relatively simple one, and we're going to look at the LDIR command. Now, this example will work on most of the systems, so let's run it on the Enterprise, because I don't think the Enterprise has had enough attention recently. So let's fire that up. And let's run the example today. Okay, so this is our first example here, and you can see we've got a series of memory dumps on the screen. And what we've basically got is the first line here is the starting memory, and then we've run some commands on this memory range. And we've used two commands here, LDIR and LDDR. And these actually use the three main register pairs, HL, DE and BC. And in a lot of ways, these are the commands that these pairs get their names from. It's often said that HL is a source memory address, DE stands for destination, that's often sort of said, and BC is for byte count. And the LDIR and the LDDR commands very much take this to use. What these commands do is they do a sequence of data transfers. They will transfer BC bytes, so in this case 6 bytes, from the HL source, in this case test data, to the DE destination, which is test RAM in this case. So what we've done here is we've transferred 6 bytes from test data to test RAM. Now, test RAM is being shown to the screen here. This is this 0 area here. So that is the starting position with nothing in it. And test data is this data here. So this is our test data here, the values 1 to 6 here. And we're going to transfer, coincidentally, a total of 6 bytes with this LDIR command. So this command in one go will transfer 6 bytes. So you can see our starting position here was the 81F0 range, which is the test RAM range, was all zeros. But then after the LDIR command, 1, 2, 3, 4, 5, 6 at the start of the range, and you can see the rest of the range is empty there. So this LDIR command has transferred these 6 bytes from HL to DE. And basically this is like a loop where HL goes up by 1, the byte is loaded from HL and written to DE, and DE goes up by 1, and then BC goes down by 1 until BC equals 0. So if we check the values of HL, BC and DE after this LDIR, the HL would have gone up by 6, DE would have gone up by 6, and BC would have been set to 0. But the accumulator isn't actually changed by these commands. So that's something quite interesting. So as I say, we've done that first LDIR, which stands for load, increment and repeat. So this goes up in memory. So with each transfer, HL goes up by 1 and DE goes up by 1. Of course, BC goes down by 1 because BC is the byte count, which always goes down. But we have an alternative, LDDR, load, decrement and repeat. Now, this one will load from HL into DE, HL being the source and DE being destination, and it will decrease the byte count in the same way as LDIR, but this time HL and DE both go down by 1. So in this case, we're setting the HL source to the end of our data range, the DE destination to the end of our memory range, and our byte count to 6 again, and we're using LDDR. Now, before, the end of the memory range was all zeros. You can see that bottom line is all zeros. But after the LDDR command, well, that range has again been filled with 6 bytes going 1, 2, 3, 4, 5, 6. And the reason that happened is we pointed not just the destination in DE to the end of our range, 15 bytes on from the start, because each of these lines is 8 bytes, so that's why we've done 15 bytes, but we've also pointed the source to the end of the range here. And you can see we've got a pointer here to the end of the range. So that has basically pointed the HL source to this 6 byte here, and then after each write, it's gone down by 1 and written that byte. And also the destination memory has also gone down by 1. So that's why we've created that memory range there. That's how we've transferred that memory there. Now, these are a single command here, and they are a fast command. They're a really fast way of transferring memory, and faster than creating our own loop where we repeatedly loaded in the accumulator from HL, wrote it to DE, and then did our increments of HL and DE. It's a lot faster than that, but it's not an instantaneous command. You know, the LDIR command isn't as fast as an InC command. You know, it might just be 1 byte of memory in our compiled program, but because the compiled command is actually going to do a lot of other tasks as part of its running, it isn't as fast as, say, a single byte command like an InC or a no-op command. It's much slower. Now, there is a trick that we can use with LDIR and LDDR to actually make them faster, and this is something known as unwrapping of loops and things like that. Now, unwrapping is where we take a command or a sequence of commands that would usually have a loop in them, and instead of using that loop, we remove the loop and we just put repeated commands over and over again. This takes a lot more memory in the size of our program, but because there's no loop and the processing of the loop and the comparison of in the loop would take a little bit of time, we've removed that time, and that means we are able to make our program faster at the cost of memory. And we can do this with LDIR. LDIR is load, increment and repeat, but if we don't want to have that loop and check that BC, we can use the shorter LDI command. This will load from HL and write to DE again, but it doesn't use the byte count and it doesn't do the loop. So when we do 3 consecutive LDI commands here, we're actually transferring just 3 bytes because there's no decrementing of BC and repeating until it reaches 0. So this command is slightly faster than an LDIR with a byte count of 3. So if you're desperate for speed, which you might well be if you're doing things like transferring bitmap data to your screen, for example, this is a very fast command, and as I say, it's just sacrificing a little bit of memory, but that is the sacrifice we often make. So what we're doing here is we are using the example data test data 2. Well, here's test data 2, FFEE, DD, CC, and so on. And we are transferring 3 bytes because there's 3 LDRI commands, and we're transferring to test RAM again. So test RAM, after we last saw it, had 1, 2, 3, 4, 5, 6 at the start of its range. But after 3 LDI commands, we've ended up with FFEEDD. And of course, these commands don't use the BC register pair at all. They don't care what value is in that pair. So as I say, we don't even need an extra line as part of our sequence here. So again, that might be another reason why, in this case, actually loading BC with a value of 3 would add an extra 3 bytes. And so 3 LDI commands are actually shorter in memory as well. Now, if we were doing 300, they wouldn't be shorter, but they certainly would be faster. So, as I say, this is a command that's worth bearing in mind, a shorter, sort of more simplified version of LDI and LDD, but with the advantage of speed. Now, we used LDI there, but we can also use LDD, exactly the same as LDDR without the repeat. So we've again specified to the end of our ranges here, and here we've transferred CC, AA and 99 to the end of our range here with those LDD commands there. Now, again, with all of this kind of thing, what I'd suggest you do, as I generally would always suggest really, is if you want to sort of see the full range of commands that are available to you, please check out the cheat sheet. If we go over here and have a look at the cheat sheet here. So you've got a wide variety of commands here, and you can see them all here. So you can see we've got these commands here, the load increment, load decrement commands, and there's some details there of how the different registers are affected by these commands. So you can check that out, and as I say, it's a good way of just reminding yourself what options are available with these commands that are maybe a little bit tricky. Okay, so that's our loading, incrementing and loading and decrementing there. As I say, really fantastic commands available to us on the Z80. They've only really been left to this stage because I thought it was more important to go into the sort of more simplistic mathematical commands before more advanced command like this. But as I say, this command is very, very handy, and I'd certainly strongly suggest you use it. Now, the next thing we're going to be discussing is the rather annoying concept of ports, and unfortunately this is very, very hardware specific to the system you're working on. Firstly, because depending on your hardware, the devices on those ports will be completely different, but actually as a quirk of the Z80, the number of ports the system will have will vary depending on your system. Let's go over to our screenshot and let's just discuss the concept of ports. So here we've got an imaginary system that I've sort of drawn here with a Z80 processor, and we've seen in the past that we've got memory, and the memory is a 16-bit address bus, and so this allows a range from 0 to 65535. Now we would see that as a 0 to quadruple F as our 16-bit hexadecimal memory addresses, but there is another way that the Z80 can address things on our system. I say things because it's not memory, but it can also address hardware through it's effectively a sort of a secondary address bus, if you will. It's actually the same address bus, but there's an extra bit that switches over to a secondary set of devices. This becomes the port that we want to control, and these ports, depending on your system, will be mapped to things like maybe the video card on some systems, maybe the keyboard, and maybe some kind of sound device, a beeper speaker, or maybe an AY sound chip, who knows. As I say, this is all completely specific to the system. Now the problem is that depending on how the Z80 is wired up to the hardware of our system, the number of ports the system will have will vary. It could be 255 or it could be up to 65535, just depending on how the address lines have been wired up. And as I say, from our code there will be no way to tell this, and rather annoyingly the command that the Z80 uses, even on these systems that are wired up to 16-bit ports, looks like an 8-bit command. The command we will often see is the out and then the letter C, which is register C in brackets, and this means out a value to port C. However, this assumes that the processor is wired up as an 8-bit system, which is true of the systems like the LN Enterprise, which is 8-bit, MSX, which is 8-bit, the Master System, which is 8-bit, and the TI-83 all use 8-bit ports from 0 to 255. However, systems like the Amstrad CPC, the Computers Lynx, the Sam Coupe, the ZXSpectrum, and the ZX81, when we do the command out C, the actual register that's used is the BC pair, and they will define a 16-bit port. Even more confusingly, some devices will reply to a range of addresses, so we don't necessarily need to specify the full address on these 16-bit range systems, and also devices may respond to a variety of different addresses. As I say, it's all very confusing, but the important thing at this point to bear in mind is if you're looking at a system within this range, and if you're not looking at a system on this range, i.e. one that I've not covered here, you need to bear in mind that your system might be using 16-bit addresses for its ports, and in that case the value in B, or the BC pair if you prefer, will actually be being used in the out commands, and that will be, if you're looking at code examples online, you might see BC being loaded and you can't see where the B part is being used. Well, that's going to be what's going on there. So that's just something to be aware of, and we're going to see some examples on a couple of different systems, and we're going to look at some ones that use 8-bit ports and some that use 16, and I'll try and make it a bit clearer as we go along. Anyway, let's go over and let's try the in and out command. Now the in command is for reading data in from hardware, so for example reading keys from a keyboard, and the out command is for sending data out to hardware, for example making a sound or changing a color. Now, as I say, these are all very hardware specific, so we're only going to see a few, and we're only going to do a very limited set of things, because what I'm trying to tell you about today in these examples is the out and in commands, and not about the hardware itself, because that's what my platform specific series is about. Okay, well, let's fire this up on the Sega Master System. Okay, so, well, what have we done here? Well, what we've done, let's just pause this because it might start going weird soon when it fills the screen. Okay, well, what we've done here is we've loaded the HL pair with the value C000. we've loaded the C register with BF, and then we've used the command out, and we've sent the L part of the HL pair, which is going to be 0 in effect, to the port C, which is port BF in this case. And then we've waited a while just because the hardware might take a little time to respond to that. And then we've outed the H register to port C, again to port BF. Now, on the Sega Master System, this is effectively sending the VRAM memory address C000, which on the Sega Master System happens to be the palette settings. So as I say, you need to look into the hardware itself to understand what these addresses do on this system. But as I say, all I'm trying to tell you at this point is the out command here is sending the value in the L register to the port in the C register, and you know it's the port because it's an out command, and the brackets denote that it's the address in the C register that is the port we're writing to. So there we've done to write 2 ports there of data using the C register. But on an 8-bit port system, we can also specify a port as an 8-bit value in brackets. So here we've loaded the accumulator with this value here, this 0 value here, and then we've outed the accumulator to port BE. Now we selected an address with BF, but we're now writing a value to BE, and outputting a value to BE after selecting the address C000 with the port BF actually sets the color for one of our palette entries. And what we've done here is we've changed our screen color to black here. Now we can confirm this because the configuration of this byte is in the bit format here. So you can see that the bottom 2 bits are the red component. So if I just change the bottom bit to a 1 and I run again, well, now you can see we've got a kind of dark red background here. So that's the effect outing that value to port BE is after we've selected the address of color 0 by outputting the pair to the port BF here. As I say, these are 8-bit ports, so the out C command with C in brackets here specifies that as an 8-bit port. Now, what we've done next is we've actually done an in command, whereas out will send a value from a register to a port. Well, in will read in a value from a port into a register. We've specified our register as a numeric value here, not a port. We could have done in C as well if we had C set to the right value, but we've done in from DC here in hexadecimal, and DC is actually the joystick port. The Master System's super easy for reading values in from our hardware here. So we're repeatedly reading in from our joystick, and I've got our joystick configured to the keyboard. So if I press up here, you can see that the FF has gone to a BF, and if I press the down, it's gone to a 7F. And so that's how we can write data out to hardware with the out command and read data in from hardware with the in command. So those are some simple examples on the Sega Master System, which, as I say, has 8-bit ports. Well, this time we're going to try the ZXSpectrum, which has 16-bit ports. Let's try the ZXSpectrum. Okay, let's fire this up. Okay, let's just pause this here if I can. So what have we done this time? Well, we've done some similar commands this time on the ZXSpectrum here. So first of all, what we've done is we've sent the value of 3 to port FE. Now that might look like an 8-bit port, and the ZXSpectrum is 16-bit ports. But this is where things get a little bit tricky, because the ZXSpectrum will actually respond to a 16-bit port with any value, with any top byte value, as long as the bottom byte value is FE. So what we've effectively done here is we've set the color of the border here. We've set it to a value of 3, which has set our border to a magenta color. And then what we're doing here is we're going to read in from a port. Now in this case we need to specify a 16-bit port. So although our command is in A, C in brackets, and that would look like it's going to read in from port C, on the ZXSpectrum it's a 16-bit port, but it's actually going to load in from port BC, and we've specified the port as 7FFE. So that's the 16-bit port that this in command is actually going to be reading from. Now what the command should really be, if it was going to be honest, is in A, BC in brackets, but that will not compile on this assembler. Interestingly enough, Z80 does use that syntax, but the classic Z80 does not. Now you might think, well, that's terrible, why is the assembler lying to me? Well, the assembler simply doesn't know. The Z80 specification did permit for this 16 8-bit port wiring, and it's nothing to do with the code that's compiled. It's the actual wiring of the hardware that defines how the ports work. As I say, it's all very specific, and unfortunately, while it was in some ways sort of suggested that the Z80 have 8-bit ports, it was documented originally that it could be wired up to use 16-bit ports, and in that case it would use B and C as a combination. So it's rather unfortunate the assembler syntax is rather confusing for us beginners when we get started, because it really confused me originally. So anyway, we're once again reading in from 7FFE, and this is part of the keyboard. It doesn't read in the entire keyboard, but it reads in a little bit. And so if we press the space key here, we should see the numbers on the screen change. So if I press space here, you can see the BE goes to a BF. And there'll be some other keys on there. For some reason, the M key is also there. You see it changed to a BB, and so on. And once again, as I say, unfortunately on the Spectrum, if you want to read in the entire keyboard or certain combinations like QAOP for gaming, it can be a little bit of a pain. You might need to read in from lots of different ports. And as I've said before, if you take a look at my platform specific series, I do have examples and sample code you can use to do that kind of thing. Once again, we're not here to discuss how to read in the keyboard. We're just here to discuss the concept of out and in on a variety of different systems for writing to ports and reading from them. Okay, so that's how we can use the in and out commands to read and write single bytes of data. But just like we had the LDIR command for sequential transfer of data to and from memory, we have some special commands like OTIR for transferring large amounts of data from memory to ports. And we also have InIR, which is an equivalent one for reading in. But for today, for example, we're just going to use OTIR, because I think when you're getting started, this one is a very instantly usable one for common tasks. For example, setting the color palette on the Sega Master System. Now, we looked very quickly last time at the fact that if we specified the memory address C000 and wrote that pair to the port BF as we're doing here, that would select the first color of the palette, the background. Now, if we write a byte to the port BE, then that will set that color. But if we write a sequence of colors, for example, these bytes here to that port, we can effectively set the full 16 color palette all in one go. And so what we're doing here is first we're using the out command with 2 bytes again to specify memory address C000, which is the start of the palette memory. And then we're specifying the HL source as palette data SMS. We're specifying the C register, which is the port destination, to port BE. Now, if you remember, we used port BE before when we were setting our color up here. So we're doing the same thing again. We're just going to do a sequence of colors, and we're specifying the byte count in B. So our B is our byte count, C is our destination port, and HL is our source memory address. DE is not used by this command, and OTIR will repeat until B reaches 0. So if we compile this and run this here, well, now we've got a hello world message, but we've actually changed our palette, and we've used this palette that's defined here, and we can confirm this by messing with some of the color values. So for example here, if we look at our last entry here, we can see that this is a sort of a blue color, and this has been used for the font here. But if we change this value, for example, if we just changed it and changed the last 2 bits to 1s, each of these bit pairs is a single color channel. So this will change our font to a white color from a blue color. So we've effectively set all 16 palette entries with a single OTIR command. Now the problem with this command is, you might have guessed, is if we tried to use this command on a Z80 system that is wired up for 16-bit ports like the Amstrad CPC or the ZXSpectrum, well, that B byte count is going to be used as part of the port address. So this command doesn't really work on those systems very effectively, but it's a fantastic command for 8-bit systems, especially for systems like the Sega Master System and also the MSX, where you can use it for setting nice sequences of palettes by doing a command like this. So there we go. So that's how that command can be used. And once again, if you want to see, there are a range of commands. If we just look at the cheat sheet, you can see there's some in incremental commands and there's some out incremental commands. And like before, where we could do LDI without the repeat, there is an OutI command which will not repeat, and you can actually to some extent use that on the Amstrad CPC because you can correct the B register after each execution of that command. The Chibi Akima's game did that for very fast palette switching during the mid-screen redraw. But as I say, at the point you're just getting started, you don't actually need to use any of these kind of commands. You could just use a normal loop and just use a sequence of out commands. But I wanted to show you that they were available and point out just how flexible they are. So in that example, we were setting the palette on the Sega Master System. A system with some parallels to the Sega Master System in terms of hardware is the MSX. And this time, we're going to have a look at the MSX1. And we're going to do some transfers to memory on that system. Now, the port numbers are different. The function of the VDP is quite similar, but the port numbers are different. So in this case, we're going to write to VRAM address 5800 in hexadecimal. And on the MSX, we need to use port 99 in hexadecimal to select the VRAM destinations. So we write the pair of the address we want to select, low byte first. We write the low byte of that pair to port 99, and then we write the high byte of that pair to port 99. And this is selected a VRAM destination. Now we select the memory address with port 99, and then we write bytes to port 98, and these are written into VRAM. And we're going to write a sequence of 31 bytes. We're loading B with 31. HL is our source, which is tile data MSX1, which you can coincidentally see down here. And we're going to transfer all of those bytes into VRAM. Because a write to port 98 will transfer the data to the VRAM address previously selected. 5800, as it's configured, is the screen memory. And so when we transfer these bytes to screen memory, they are going to effectively set tiles or characters, if you prefer, of the screen. And so you can see this has produced this rather interesting set of characters here, which are effectively the first 31 characters of the character map. And we can change this code and do other things. For example, if I change this and I change the byte count to 131, well, I think we're going to make a bit of a mess because, well, that's going to transfer an awful lot more data, but part of that data isn't actually defined here. So we're going to end up transferring bytes of our code. That OTIR command will, of course, repeat until B reaches 0. And so you can see we've transferred all kinds of weird things to the screen here. Now, the important thing, of course, to understand with this is because we're just using a single register for B, we can't go over 255 bytes transferred in a single iteration here. We could use more OTIR commands later on if we needed to transfer more data, but as I say, the B register, being as a single 8-bit register, is only able to transfer up to 255. But there's some practical examples of the kind of things you can do with out and in commands. As I say, reading from keys, write out and change graphics memory or change palettes. It all depends on the system, and that's where my platform specific tutorials come in, because they are intended to cover that in far more depth than we've done there. Okay, so that's all we're going to cover on ins and outs. As I say, you will come across those in far more detail when you actually start to look at whatever system it is that interests you, and the platform specific tutorials on my series, or if you're going somewhere else, anyone else's tutorials will cover that in more detail. And as I say, the main thing to bear in mind is on some of the systems you will be seeing 16-bit ports, and they might confuse you. Hopefully, if you've understood what I've said, if I've explained it properly, you'll be a bit clearer than I was when I took this on. Now we're going to discuss something different now. We're going to start discussing interrupts. Well, what is an interrupt? Well, an interrupt is exactly what it sounds like. Now, in the past, we've looked at programs which have a linear execution of code. Maybe we read in from the keyboard and then we write the character to the screen, something like that. But there will be things that will need to happen, and they will need to happen extremely fast, and they will need to happen at times that our program may not be ready to do them. One example of this is VBlank. This is the drawing procedure at the very top of the screen. So we've got a raster line that goes down the screen. When it gets to the bottom of the screen, it will jump back to the top, and something known as VBlank occurs. And in programs, quite often this is the time when you want to do things like switch palettes or maybe reload sprites into memory. A lot of systems can't allow VRAM to change during the redraw, and so these need to be done during VBlank. And because the VBlank is such a short period of time and happens very quickly, it's not going to be possible for us during our game loops to actually test for that. And so these are something known as interrupts. Now an interrupt is actually effectively like a call. In the same way as a normal call, it will push a return address onto the stack, but it will jump to a specific hardware address on our system, and we'll discuss that in a moment. But first, I want to discuss the two kinds of interrupts that there are. And there are two kinds. There are what are known as non-maskable interrupts. On the Z80, these execute to memory address 0066 in hexadecimal, and there are maskable interrupts, and these execute in interrupt mode 1 to memory address 0038 in hexadecimal. Now the difference between these two is pretty simple and is kind of explained in the description of them. A maskable interrupt is something that we can actually disable. We can mask it out and stop it for a short period. One reason we might want to do this is if we're doing something even more time sensitive, like reading in from a disk drive, that disk spinning, and we don't want sprites loading in during our VBlank or our palette changing work because we'll lose our data. Another reason might be maybe we're using the resources that interrupt handler would usually take over. For example, the shadow registers. If I want to use those shadow registers, I might disable the interrupts for a while I use those shadow registers and then enable them later on. And we have commands to do that. One is DI for disable interrupts and EI for re-enabling the interrupts later on. Now that will stop and then resume maskable interrupts. But there is another kind of interrupt known as the non-maskable interrupt. And what this means is we can't mask it, we can't disable it, we can't use our DI command to disable interrupts. The interrupt will occur whether we try and stop them or not. Now you don't tend to actually come across non-maskable interrupts very often, they're extremely rare. On the Amstrad CPC, the only non-maskable interrupt I've ever seen was the multiface 2. The stop button on the multiface 2 was a non-maskable interrupt. On some Spectrum hardware, like some of the disk emulators also have a similar button that we'll call as a non-maskable interrupt. But basically, generally speaking, you will not see them on a lot of the systems. But as I say, they are a thing. They're hard-coded into the Z80. So there's something you need to be aware of. And if you have access to low memory and you want to disable non-maskable interrupts, you can just put a return at memory address 66 and that will disable them. One quite curious use of non-maskable interrupts, though, is the pause button on the Sega Master System. The Sega Master System pause button wasn't on the controllers, it was actually on the base unit itself. And unlike the other buttons, which were read in from ports, that actually caused a non-maskable interrupt on the Master System. So if you want to control that pause button, you need to put some code to do that at memory address 0066 in your ROM to actually handle that. And I did that in my Suck Hunt game. I had used the pause button, so I had to do that. Now, as I say, mostly we're going to be dealing with maskable interrupts, and what we're really going to be covering today is how to write your own. This isn't something you're going to need to do in the early days, but if I'm going to cover the Z80, I need to discuss what interrupts are so you know what they are and what's going on behind the scenes. And as I say, if you're trying to use those shadow registers, you need to know about them so you know why you can't use them and what you need to do to be able to use them in a lot of cases. Now, another important thing is we're going to be looking at interrupt mode 1, which the maskable interrupts cause a call to memory address 0038. Now that is fine on a system like the Amstrad CPC where that's memory. It's also okay on the system like the Sega Master System where we're writing our entire own ROM and we can take control of that area. But on other systems, to some extent the MSX1 and very much the ZXSpectrum, we can't write to that area. That area is ROM, it's read only, and we can't change it. And for that reason, interrupt mode 1 might not be available to us. There's an alternate mode, interrupt mode 2, but it's much harder to use. I have a specific tutorial on interrupt mode 2, so if you need to use your own interrupt handler on a system like the ZXSpectrum, that's probably the best solution for you, and please see that specific tutorial. Today we're just going to be looking at interrupt mode 1, and we're going to be seeing some source code examples of that. We're going to look at the Amstrad CPC, and then we're going to look at the SAM Coupe, and we're going to be playing with ports at the same time. Okay, so what are we doing here? Well, first of all, we're going to change the interrupt handler, so we need to make sure that an interrupt doesn't fire while we're changing that interrupt handler. So we do a DI, that's disable interrupts, and that will stop any maskable interrupts occurring. We're then going to write to memory address 0038, which is the interrupt mode 1 maskable interrupt handler. Now, what we're going to do is we're effectively going to write a jump command at that memory address. When an interrupt occurs, it's basically a call to memory address 0038. And so we're going to jump to our own memory address. So we've got a command. So we're writing a byte C3 here, which is the equivalent of a jump command. And you can see that on my cheat sheet. If you take a look at the cheat sheet, you'll see the byte commands that each command compiles to. We're then loading the address of our interrupt handler. This is our interrupt handler. And we're writing the 16-bit address after the jump command. So that will make memory address 0038 jump straight to interrupt handler CPC. And that's what's going to happen when our interrupts occur. Now, we've now taken over the interrupt handler for the maskable interrupts, and because we've done that, we can now do whatever we want with those shadow registers. Before, the interrupt handler on the CPC would have been using them, but now we're the interrupt handler on the CPC, so we can do whatever we want with those shadow registers. So we're switching in the shadow registers here, and then we're loading the shadow HL with 5458 here, and then we're switching back to the regular registers. Okay, we're going to use this in our interrupt handler, and then what we're doing is we're turning interrupts on. Now, another tricky thing with regards to interrupts is the interrupts, what happens during interrupts and what we need to do during interrupts is again very hardware specific. On the Amstrad CPC, if we disable interrupts and then we enable them and an interrupt was missed during that time, the interrupt will immediately fire and then the interrupt will occur once. On a system like the MSX, it will also immediately fire, but on the MSX, our interrupt handler actually has to clear the interrupt, otherwise it will keep firing forever. So we need to make sure our interrupt handler does that. On the other side of the spectrum, quite literally, is the ZXSpectrum. If an interrupt should have occurred while we had interrupts disabled, it will simply be missed, and the next interrupt that occurs would have to occur during the enabled time for it to occur. And the problem with that is on a system like the Amstrad CPC, if we're playing music during our interrupt handler and the game gets quite slow and we have to disable interrupts and we miss some interrupts, they'll all pretty much happen as soon as interrupts are re-enabled, but on the Spectrum they'll be simply missed and the music will be significantly and noticeably slower. So disabling interrupts on the ZXSpectrum is a serious problem when you're playing music. Okay, anyway, as I say, I know that's probably a bit complex for you at this stage, but I'm trying to tell you all of the things I've learned through bitter experience. Okay, so we've got our interrupt handler in place, and we'll have a look at what it does in a moment. But what are we actually going to do as part of our loop? Well, we've got a loop here, and we're going to loop 255 times, and all we've got is a simple command called halt in our loop. Now, what this actually does is it stops the processor until an interrupt occurs. So if you do a halt with interrupts disabled, well, your machine's going to lock up. But in this case, what it's doing is simply waiting for an interrupt to occur and then repeating. So we're going to have effectively the result of 255 interrupts as part of this first loop. Let's take a look at what that interrupt handler does. Okay, so here it is. So this will be executed when the interrupt occurs. So first of all, for safety, we're disabling interrupts. Now, we don't actually need to do this normally, but we're actually going to manually call this later on. Interrupts are disabled automatically during the Z80's interrupting process, but as I say, we're going to call it manually later on and have some fun with it. What we're doing next is we're switching over to the shadow registers, and this is because if we didn't do this, then our interrupt handler could occur at any time during our normal code, and if it changes the normal registers without protecting them via a push and a pop or something, it will corrupt our normal code, because as I say, interrupts can happen at any time while our program is normally running. So the solution to this is the shadow registers. They're faster than pushing and popping things, so that's why we're doing that. And what we're doing here is we are going to change the palette of the background, and to do that on the Amstrad CPC we use out commands, but again we need to use BC, we need to use the 16-bit port, so we're specifying the 16-bit port 7F00 here, and we're going to select the color 0 here, and then what we're going to do is we're going to set that to the value in the L part of HL. And these are hardware color numbers, so we're going to set it to 58 the first time this runs. But then what we're going to do via this combination here is we're going to swap H and L, and then we're going to return. And what that's basically going to mean is the next time this runs, that HL shadow pair is going to be the opposite way around. So we're going to set the colors to the opposite colors next time. So we're going to swap between 54 and 58 each time the interrupt handler occurs. And we're going to do that 255 times. And then what we're actually going to do is we're going to disable interrupts, so no interrupts will fire again, and this time we're going to use the RST38 or RST7 as it might be called depending on your assembler, but this is effectively calling directly to our interrupt handler manually, and that's why we needed to manually disable the interrupt here. And so we're going to see what happens when that interrupt handler fires at full speed, and it's going to be quite different. Okay, so let's fire up our CPC emulator here and let's see what happens when we run this piece of code. So hopefully we're going to see something a little bit spectacular. Okay, so I've just paused the emulator there and we're going to actually just have a quick look at what's going on. And just so we can be clear, I've got the debugger open. Now, I've not covered how to use this in this series because this is a multi-platform series and I didn't want to go into the Amstrad CPC's debugger, but I do have my original series which went into great depths on this. But what I want to show you today is how the interrupts are firing on this system. And again, just like with ports, how interrupts occur is different on each system. And on the Amstrad CPC, there isn't just one interrupt per screen, there's actually 6. So if I repeatedly continue the code here, there's one interrupt there, there's one interrupt there, there's one interrupt there, one interrupt there, one interrupt there, and a final interrupt there. So what is actually happening here? Well, each time our interrupt handler occurs, we are setting the color of the background and we're swapping the palette each time. And so each time the interrupt has occurred and it's being drawn by the emulator with these lines here, we're swapping the color. And so we've made this zebra stripe pattern here. And what you could do is, if you were being clever, is you could change more than just the background color, and that's what Chibi Akamas did. It switched the colors at various parts of the screen, and this allowed the screen to simulate more than 4 colors on the 4-color screen. The game was only in 4-color graphics mode, but it would have up to, I think it was about 12 colors on screen because it was doing this trick. And this is taking advantage of the fact that the interrupts occur 6 times per screen, and this allows us to switch the colors in various places with reasonable precision. Although if you look at Chibi Akamas, you'll see that the color breaks would tremble slightly, and that was because there's various disable interrupts when I was using the shadow registers for sprite drawing and things like that. So that's what our interrupt handler does when it runs normally as part of the halts at the proper predefined time. But when we disable interrupts and we manually execute it with an RST38, well, the colors are going to switch at crazy speed, and so we get that rather weird effect there. Not particularly useful, but I'm just making the point of showing the difference between properly timed interrupts and changing the colors at completely almost random times, and also the fact that we can use RST38 to manually fire an interrupt on the interrupt mode 1 systems. So there we go. So that's what we can do on the Amstrad CPC with its 6 interrupts per screen. Well, let's take a look at a different system. Let's have a look at the SAM Coupe, which has just 1 interrupt during VBlank. But again, we can use this. So once again, we're doing the exact same thing here. We're disabling interrupts. We are now going to basically page in some memory to the low area, because the SAM Coupe starts off by emulating the Spectrum, which is ROM at low area. But we want to write to the low area so that we can create an interrupt mode 1 interrupt handler. So what we're going to do here is we're sending this byte code here to port 250, which is selecting RAM at the low area, and we're putting our interrupt handler in the exact same way as we did on the Amstrad CPC. We're then doing 250 iterations, but this will take longer on the SAM Coupe because there's only 1 interrupt per screen, whereas there were 6 on the CPC, and then we're again going to fire them as fast as we can. Well, what's our interrupt handler going to do? Well, something kind of similar here. What we're going to basically do on this system is we're going to write the value in the register B to port C, and port C is going to be set to 254. These are of course the shadow registers, so this doesn't affect anything in our main code. They're the shadow registers, but we're going to be writing incremental values to port 254, which is the port that controls the border and also the sound. So this might make some rather annoying sounds. Okay, let's fire this up and let's see what happens. Okay, so we've got some sound and we've got a flashing border, quite crazy flashing, but then as we're now into our RST very fast mode, and you can see we've got this quite stripy, fantastic rainbow effect there. And you'll see things like that sometimes during cassette loading, and as the interrupts of the cassette are interfering with the code, you'll see the strange rainbow effects there. But anyway, I thought that was just a little bit of fun to show how the interrupts were handling on this system. And as I say, because the same port actually handles sound and also the border, when we write random values to it, we do get some rather weird effects there. Now, we haven't looked at it today because we didn't need to, but there is a command called im1 that selects interrupt mode 1. That's the default mode on the systems we've looked at today. There's a command im2 which selects interrupt mode 2, which I've got as I say, a much more detailed tutorial on because it's very complex. There's also an interrupt mode 0, im0, which is to my knowledge, completely useless for a programmer of any of these systems. If you were doing hardware level stuff, it might be more interesting to you. But I think it's outside of what you'll ever need as part of regular programming. I know of no way you can effectively use it. Anyway, I hope you've enjoyed this today. If you have, hopefully you've liked and subscribed by now. Hopefully you've enjoyed what you've seen. As I say, loads more content on my channel, platform-specific tutorials, multi-platform tutorials, which go into more detail on tricks and techniques with the Z80, and also the advanced series where we look at things like binary coded decimal again. More that you can do with the processor that aren't the essentials to get you started. Hopefully you've enjoyed this and you're going to continue with your Z80 programming, but if not, then I do have tutorials on a wide variety of other CPUs. If you would like to try 6502, 68000, 8086, ARM, PDP-11, TMS 9900, I'm going to be doing MIPS later on. I've done RISC-V as well. I've got a lot of other tutorials on assembly languages, so if you're feeling like something different, maybe take a look at one of those as well. But whatever you decide to do, I wish you all the best with your programming projects. Thanks for watching today, and goodbye.